Alright, today we're going to have a look at further trigonometric integration. Now in the HSC for the old syllabus we were always told when to use the T formula, and it's likely that this will continue. Otherwise though, it does take quite a bit of practice to recognise when to use the T formula when integrating. Now T formulae are one of our last methods, as many integrals involving trig functions can be solved more easily through other types of substitutions and other methods. Now once you've substituted for t, the integral can just be rearranged into one of the standard integrals and then solved. Remember though, if you're using an indefinite integral, remember to rewrite your answer in terms of the original variable, and if you're doing a definite integral, you need to consider, if you're finding x, for example, that it's tan of x on 2, and you need to account for that. So evaluate the integral of dx on 1 plus cos of x dx using the t formula. So we know that the t formula for cos of x is 1 minus t squared on 1 plus t squared. So this is the integral of 1 over 1 plus 1 minus t squared on 1 plus t squared. And we've still got a dx, but we do have to change this. So we know that t is equal to tan of x on 2. Now that would mean that t is equal to a half of sec squared x on 2 dx. Now there's a big problem with that because we don't have any trigonometric functions left in the integral, but our t to x thing does. So we need to use our t formula to simplify this. Now there's a number of different ways of using the t formula here. You could realise that sec is 1 on cos, so this is going to be 1 over 1 minus t squared on 1 plus t squared all squared. But that's going to be, and you'd have to account for that x on 2, so that would make it much more difficult. The easier way, and this is what you're going to do for most of these questions, is to realise that sec squared x is tan squared x plus 1. So this is a half of tan squared of x on 2 plus 1. However, we've defined t to be tan of x on 2. So this is a half of t squared plus 1. Then we've still got a d, the t here, and a dx here. We're going to leave that for now, and we're going to have a go at simplifying this integral. So if we multiplied this up to here, and then put that up to there, we're going to have, this is the integral of 1 plus t squared over 1 plus t squared plus 1 minus t squared. So it's going to be 2. 1 plus 1 is 2. Excuse me. dx. So what we're going to try and do with this integral is we're going to try and replace this and this with dt. And in fact we're almost there, because we can say this is the integral of 1 half times by 1 plus t squared times by dx. So we can just replace this with dt. This is just the integral of dt, because that is dt there. So this is the integral of dt, and the integral of dt of course is t plus c, but t was tan of x on 2, so this is tan of x on 2 plus c. Now there's probably many other ways that you could do this integral. So you might be able to do some sort of u substitution. The reason t, and the reason you'd know to use t in this case, is there's not actually a squared here on the cos, so it's not as easy to use those squared identities and manipulate those. But if it's just 1 plus cos of x, it's quite tricky, so maybe use a t substitution. Again though, as I explained previously, in the old syllabus they would always tell you when to do that. So example number 2, we're looking at the integral of 1 over 4 plus 5 cos of x, and we're using the t substitution. Now I'm pretty sure this is a HSC question, and it actually did say using t substitution or otherwise. Just remember though, when it says or otherwise, 9 times out of 10, the or otherwise is much more difficult. And I've only ever seen one question in the past, which was an integration by parts question it was an extension 1 question where integration by parts was a tad easier. So usually the or otherwise means harder. So let's use our t formula. So this is the integral on 1 over 4 plus 5 lots of 1 minus t squared on 1 plus t squared. And let's use our substitution. So t is 10 of x on 2. Now I've already proven in the past that that means dt is a half of 1 plus t squared dx. So let's simplify that. It's going to be 4, if we times this up to here, 4 plus 4t squared plus 5 minus 5t squared. So that's going to be 9 minus t squared. And of course, we're putting our 1 plus t squared on the top. And that's times by dx. Now the next step here is to somehow get rid of the dx, because we can't integrate that until we get rid of the dx. It needs to be in terms of dt. So what we might do here is we might put a cheeky little 1/2 here. If we do that, we need to put a 2 here, and there we go. Now this here is now that. So we can say this is 2 lots of the integral of dt on 9 minus t squared. Okay. Now this is where we're going to use our knowledge of integration by parts, which we saw in a previous video. So this is 2 lots of the integral. We might say that this is 3 minus t and then 3 plus t. And that's because this is equal to 1 over 3 minus t, 3 plus t dt by our integration by parts. I'm going to use that magic method. So what can we do to make this 0? To make this 0, we can put a 3 here. Oh, we might do the second bit. So we can put a 3 here to make that 0. So we're going to put a 3 here. So this is going to be 1 over 6. So this needs to be 1 over 6. And then to make this 0, we need to make this minus 3. So we're going to put minus 3 here. Again, that makes that 6. So this has to be 1 over 6, and there's a plus in the middle. So this is simply equal to 2 over 6, the integral of 1 over 3 minus t, plus 1 over 3 plus t. Okay. So this is just a nice and easy ln integration. So if we were to integrate this, it's going to be 1/3. Now we ideally would like to have a negative on the top, and that's because the differentiation of minus t, or the differentiation of this on the bottom is, actually no, ignore me. So the differentiation of t is equal to 1, so we're actually good on the top. So the differentiation of that is going to be ln of 3 minus t plus ln of 3 plus t plus c. And we're done. Okay, some further trig substitutions. So another method that we can do when nothing else works is use a trig substitution. We'll normally be told in an exam when to use a trig substitution, as they're rarely needed. Often we can use a u² substitution, as they save a lot of work, and trig substitutions are often quite long. Trig substitutions can be found whenever the integrand involves a square root, including the denominator, or when the radicand is the sum or difference of two squares. And this might involve completing the square to become quite obvious as well. And sometimes we also use, we draw some right-angled triangles and have a bit of fun with that. So example 3 of the video, we're looking at the integral of x cubed root 1 minus x squared. And we're using the substitution x is sec theta. So first of all, well, if x is sec theta, we know that the differentiation of sec theta is sec theta tan theta. Let's just have a go at substituting that in. This is the integral of sec cubed of theta times sec squared x minus 1. Now sec squared x minus 1 is tan squared x, and the square root of tan squared x is tan of x. So I'll say that again. If x is sec theta, then x squared minus 1 is sec squared theta minus 1. Sec squared theta minus 1 is tan squared of theta, and the square root of tan squared of theta is tan of theta. And then we're just multiplying. We're replacing that dx with this. It's a bit different because we're not doing a u substitution, we're doing an x substitution. So we're replacing dx with sec theta tan theta to theta. So this is the integral of sec 4 theta times by tan squared of theta to theta. Now to do that, we might want to realise that the differentiation of tan of theta is sec squared of theta. So we might want to rewrite this as sec squared theta tan squared theta times by sec squared of theta again. And we've done that because actually sec squared theta is 1 plus tan squared of theta. So this is equal to 1 plus tan squared of theta times by tan squared of theta times sec squared of theta. And if we have a go at expanding that, that's a terrible sec squared there, sec squared of theta. If we have a go at expanding it, that's going to be the integral of tan squared of theta sec squared of theta plus tan 4 theta sec squared of theta to theta. So first of all, to do this, we're going to have a look at the integral of tan squared of x sec squared of x. Now to do that, we do know the integral of tan x sec of x is sec of x, but we don't know the integral of tan x sec squared of x. So we might let u equal tan of x, or tan of theta in this question, which means du is sec squared of theta to theta. So we can see here that that is going to be du, and this is going to be u squared. So of course our answer is going to be u cubed on 3, which is tan cubed theta on 3. Same idea here. If we let u equal to tan theta, that means du is sec squared theta to theta, which is that bit right there. So this is going to be u to the power of 4 on 4, and if we integrate that, we get u to the power of 5 on 5. So I'll say that again. U is tan theta, which means du is sec squared theta to theta, which is this bit here. So we can replace this with du, and this is going to be u to the power of 4. So if we integrate u to the power of 4, we get u to the power of 5 on 5, and u is tan of theta. So this is tan to the power of 5 theta on 5 plus c. But we can't leave that as our answer because we used the substitution x is equal to sec theta. So we need to somehow manipulate sec theta so I get tan of theta that I can then replace it with x's. And we don't want any trigonometric functions to be in this answer. So I can't use arctan of something equals x, for example, because the question only involved x's. So I have to get rid of all of the trig functions. I know that sec squared of x is 1 plus tan squared of x. So let's say x squared is equal to sec squared of x, or sec squared of theta, which means x squared is 1 plus tan squared of theta, which means tan squared of theta is x squared minus 1, which means tan of theta is the square root of x squared minus 1. So we can say this is the square root of x squared minus 1 to the power of 3 on 3, plus the square root of x squared minus 1 to the power of 5 on 5 plus c. Okay. Last example for today's video, and this question is going to use a triangle, and there's a number of different ways of solving questions like this, and often on our last resorts with these types of questions we're going to use a right angled triangle, and we'll see why in a second. So we're looking at the integral of 1 over x squared plus 4 plus x squared using the substitution x is tan theta. Automatically when I see this question, I think to myself, I know that 1 plus x squared is 1 plus x squared is equal to sec squared of x, and square root sec squared of x, you get sec of x. Now I think there could be a little mistake in this question. I think this is meant to be 2 tan of theta. So if we let x equal 2 tan of theta, that means dx is equal to 2 sec squared theta to theta. So if we have a go at integrating this, it's going to equal, well, 2 tan of theta squared is 4 tan squared of theta. So this is the integral of 1 over 4 tan squared theta. Now, 4 plus x squared is going to be 4 plus 2 lots of tan of theta all squared, which is 4 plus 4 tan squared theta, which is 4 sec squared theta. And if you square root 4 sec squared theta, you get 2 sec theta. So this is times by 2 sec theta. And we're timesing by 2 sec squared theta to theta. So we've replaced this dx with sec squared theta to theta times 2. So we can kill that 2, that sec, and that sec. And we're left with sec theta to theta over, we might take the 1/4 out there, make that an integral, over tan squared. Oh, don't need to theta there, over tan squared. Okay. There's a problem with this because if it was a tan on the bottom and a sec squared on the top, it would be nice and easy. It would be the natural logarithm of tan. But we've got tan squared on the bottom and sec on the top. So we might want to remind ourselves, okay, what else can I do? I know that tan squared is 1 plus sec squared of theta. Does that help me? Probably not, because I can't at all factorize 1 plus sec squared of theta. I can't use partial fractions because I could only do that if it was 1 minus sec squared of theta, and I could use a difference of 2 squareds. So we're going to think, okay, there is a relationship between sec and tan and all of these functions, and that's because sec is 1 on cos and tan is sine on cos. So this is going to be 1 on 4 integral of 1 on cos on sine squared theta on cos squared theta. So that will die with that, and we're going to have cos theta on sine squared of theta. Okay. We're almost there because I can say that this is equal to 1/4. Now I'm thinking maybe we could use 1 minus sine squared, 1 minus cos squared theta, and then use a difference of 2 squareds. But alternatively, we might try a different approach. We might say that this is equal to cos theta times by sine theta to the power of minus 2 to theta. And what I might do is I might go let u equal sine of theta, because we're going to we notice that outside of the brackets we've got the differentiation. So du is equal to cos theta to theta. So let's say this is equal to 1/4 the integral, that and that become du. So this is u to the power of minus 2 du, which is 1/4. It's going to be u to the power of minus 1 times by minus 1, which is 1/4 sine theta to the power of minus 1, and we're going to put a negative out the front. So we've added 1 to the power divided by the new power of minus 1. So the answer is 1/4 sine theta. Okay, so we've just discovered that this integral is equal to 1/4 sine of theta. But that unfortunately is not an acceptable answer, because we've used the substitution x is equal to tan of theta. And we have to somehow turn sine of theta into something just involving x. We can't turn it into tan is sine on cos. We have to just involve x. So here we're going to use a cute little triangle. We're going to say this is theta here, which means that is x and that is 1. And actually, we actually made x equal to 2 tan of theta. So we're going to say tan of theta equals x on 2. That's just a little mistake in the initial question. So x was 2 tan of theta, which means tan of theta is x on 2. So using our trig ratio, that's x, that's 2, which means this is the square root by Pythagoras' theorem of x squared plus 4. So therefore sine of theta is equal to x over the square root of x squared plus 4. So we're going to use that and go that my integral is equal to 1/4 times by 1 over x over the square root of x squared plus 4, and of course plus c. Now that's nice and easy. That is just the square root of x squared plus 4 on 4x plus c, and then we had a little minus out the front. So that's our answer there. Alright, thanks for watching.